Lesson 9-3 Scientific Notation, and in this lesson you learn to express numbers in scientific and standard notation and to find products and quotients of numbers expressed in scientific notation. Why is it important? Because you can use scientific notation to express the solutions to many problems. Let's take a look at this real-world application in transportation. The numbers of passengers arriving at and departing from some major U.S. airports for a recent year are listed in the table below. O'Hare International in Chicago is 65 million, which is the biggest one. Again, all the way down to Logan International in Boston, which is 24 million. Okay, in LA we have 48 million. Okay, arriving and departing for a particular year. Okay, so when dealing with very large numbers, keeping track of place value can be difficult. So for this reason, it is not always desirable to express numbers in standard notation, as shown in the chart. Large numbers such as these may be expressed in what we call scientific notation. And this is where we define scientific notation. So scientific notation is defined as a number is expressed in scientific notation when it is in the form of a times 10 to the n, where a is less than or is greater than or equal to 1 and less than 10, and n is an integer. That means a should be at least 1, okay, but less than 10, okay? And it has to be multiplied by a power of 10. So for the example, the number of passengers arriving and departing from Miami International was about 29 million people. To write this in scientific notation, express it as a product of a number greater than or equal to 1, but less than 10, and a power of 10. So we have 29 million, okay, in standard form, expressed in scientific notation, would be 2.9, because 2.9 is greater than or equal to 1 and less than 10. And to be able to reach 29 million, we need to multiply 2.9 by 10 million. Okay, and 10 million expressed as an exponent is 10 to the 7th power. So this is 2.9 times 10 to the 7th power. So scientific notation is also used to express very small numbers. When numbers between 0 and 1 are written in scientific notation, the exponent of 10 is negative. Again, let me repeat that. Okay, when numbers between 0 and 1 are written in scientific notation, the exponent of 10 is negative. Take note of that because this is where we're going to go in example B. So let's express 98,700,000,000 in scientific notation. First copy the problem, 98,700,000,000. And then we need to find a number that's greater than or equal to 1 and less than 10. And in this case, that would be 9.87. Okay, so that would be 9.87 times, okay, 10 billion, because if you multiply that by 10 billion, we'll end up with 98 billion. So if you're not sure, just simply count the number of zeros. Okay, the decimal is in the middle of 9 and 8. Okay, so if I put the decimal in the middle of 9 and 8 right here, okay, and if we count from the very back, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 jumps to get to that decimal point. And if you notice, there are also 10 zeros right here. So those 10 jumps will become 9.87 times 10 to the 10th power. Okay? Now let's take a look at letter B. This is where it comes in. Numbers between 0 when numbers are between 0 and 1 are written in scientific notation, the exponent of 10 is negative. So we copy the problem down, 0.00000056. And then, again, we need to find a number greater than or equal to 1 but less than 10. And that would be 5.6. Okay, so 5.6 is there. Again, we count from the decimal. How many times did we jump? to get to that decimal. 1, 2, 3, 4, 5, 6. Okay, so 6 times. So that means this is 5.6 times 1 over 1000, because that's 6 times decimal to the right. Okay, or same time, 1 over, not 1000, 1 million is the same as 5.6 times 10 to the 6th power. Okay, and using our negative properties, the negative property, the negative exponent property, I'm sorry, the negative exponent property, this becomes 5.6 times 10 to the negative 6. So if you want to jump from this example to that example, simply count the number of times you move the decimal to the right, 1, 2, 3, 4, 5, 6, and simply put the negative 6 on as the exponent of 10. Okay? Let's take a look at example number 2. Express each number in standard notation. This time we're doing the opposite. We're expressing this in standard notation. So we copy the problem. And since we are expressing this in standard notation, the exponent is positive. That means we do the opposite of what we did here. So we simply move the decimal 5 spaces to the right. This becomes 345,000, because this is the same as 3.45 times 100,000. Okay, or if we get 3.45, okay, I'll do it here, and let's put it in red, 3.45. And since that's a positive exponent, we're just doing the opposite of letter A. We move it 5 spaces to the right. 1, 2, 3, 4, 5. There goes your decimal. And we simply add zeros where necessary. So that becomes 345,000. Okay? Next example B is 9.72 times 10 to the negative 4th. Copy the problem. And when you're saying 9.72 times 10 to the negative 4th, this is the same as 9.72 times 1 over 10 to the 4th power. Okay? This is a negative exponents property. Okay? And this now becomes 9.72 times 1 over 10,000. We're just doing the opposite of letter 1b, example 1b. And this is 9.72 times 0.0001, which is the same as 0.000972. A shortcut method to this is this. Okay, you get 9.72. And since the exponent is negative 4, instead of going to the right in letter A, we now go to the left. So we go to the left 4 times. 1, 2, 3, 4, the decimal there, and add the zeros where necessary. So you have 0.00972. Same thing as this one. So this is a shorter method to get to that answer. All right? Okay. Let's take a look at example number 3. You can use scientific notation to simplify computation with very large numbers and or very small numbers. Okay? And using example 3, use the scientific notation to evaluate the expression 610 times 2,500,000,000. Okay, so we want to use scientific notation. So we copy the problem down. And then 610 is the same as 6.1 times 10 to the 2nd power in scientific notation. And 2,500,000,000 is 2.5 times 10 to the 9th power. And using the associative property, we now have 6.1 times 2.5 times 10 to the 2nd times 10 to the 9th. Actually, this is the commutative and the associative properties of multiplication. And then we simply multiply 6.1 times 2.5 will give us 15.25. And this is now the product of powers property. Okay. which is 10 to the 11th power. Simply add the exponents together. If you notice, however, 15.25 is greater than 10. Remember, the first number should be greater than or equal to 1, but less than 10. So what do? We move that decimal one space to the left. This will make it 1.25, and since we move the decimal one space to the left, we add 1 to 11. So that makes it, okay, 1.525 times 10 to the 12th power, or 1,525,000,000, okay, and that is the product. In the next example, in the next one, 3b, we want to multiply 0.000009 times 3,700. Okay, copy the problem, and then we put both of them in scientific notation. This is 9 times 10 to the negative 6, and this is 3.7 times 10 to the third power. Using the commutative and associative properties of multiplication, we have now 9 times 3.7 times 10 to the negative 6 times 10 to the third power. Okay, using our rules of exponents, first we get the product of 9 times 3.7, which is 33.3, and then using the rules of exponents, we simply add negative 6 plus 3, which will give you negative 3. And if you notice, 33.3 is still greater than 10, so we move that decimal one space to the left. And since we moved that decimal one space to the left, remember we added 1 to 11. Therefore, we need to add 1 to negative 3 as well. So that this becomes 3.3 times 10 to the negative 2, or 0.0333. Okay? Let's take a look at the next example, letter C, 2.0286 times 10 to the 8th, all over 3.15 times 10 cubed. Again, copy the problem, and then we start grouping them, breaking them apart using the commutative property. Okay, this becomes 2.0286 over 315 all over 10 to the 8th over 10 to the third power. Using a calculator, 2.0286 divided by 3.15 will give you 0.644 times 10 to the 5th power using the rules of exponents. Okay, using the rules of exponents, when you're dividing exponents, you simply subtract the exponent of the denominator from the exponent of the numerator, which gives you 10 to the 5th power. And if you notice, 0.644 is less than 1. Remember, the first number should be greater than or equal to 1. So in order to do that, we need to move that decimal one space to the right. And once we move that decimal one space to the right, instead of now adding, which we did in the previous example, we are now subtracting. So we're subtracting 1 from 5 because we moved it one space to the right. Now we have 6.44 times 10 to the 4th power, or 64,400. Okay? And last example, scientific notation extensively used by scientists in fields as physics and astronomy. And this is a good example because we're going to talk about this in the end of the year when we discuss black holes. So a black hole is a region in space where matter seems to disappear. A star becomes a black hole when the radius of a star reaches a certain critical value called the Schwarzschild radius. The value is given by the equation R sub s is equal to 2gm over c squared, where R sub s is a Schwarzschild radius in meters, g is the gravitational constant, which is 6.7 times 10 to the negative 11, m is the mass in the kilograms, and c is the speed of light, which is 3 times 10 to the 8th power meters per second, or 300 million meters per second. Okay? So the mass of the sun is 2 times 10 to the 30 kilograms. Find the Schwarzschild radius of the sun. Okay? So That's what we want to find out. And letter B, the actual radius of the sun is 700,000 kilometers. Is it in danger of becoming a black hole in the near future? So again, okay, to determine if a star becomes a black hole, okay, it needs to reach a given value using that formula. So let's take a look at letter A. Use your knowledge of exponents and scientific notation to evaluate the expression for the sun's Schwarzschild radius. First, let's look at the formula. R2 sub s is equal to gm all over c squared. Okay, and this becomes 2 times 6.7 times 10 to the negative 11, which is the constant of gravity. Okay, and 2 times 10 to the 30th power, which is the mass of the sun. Okay, all over c squared, which is the speed of light. Okay, so we end up with, simplifying this further, 6 times 2 times 6.7 times 10 to the 11 uh, uh, times 2 times 10 to the 30th becomes 3 to the second power times 10 to the 16th power, again using our rules of exponents. Okay, product of a product. And this now becomes, okay, breaking it down and using the commutative and associative properties of multiplication, you have 2 times 6.7 times 2 all over 3 squared, okay, and grouping all the exponents together with the same base, 10 to the negative 11 times 10 to the 30th over 10 to the 16th, okay, will give you 26.8 all over 9. That's the multiply all these three, okay, divided by 9. And then this becomes 10 to the negative 11th all over 30, which means you add these two exponents and you subtract 16. Okay, so using a calculator, end up with 2.98 times 10 to the third power, or 2,980 meters. Okay, so the Schwarzschild radius for the sun is about 2,980 meters. Now take a look at example B, and let's see if our sun is in danger of becoming a black hole in the future. Since the actual radius of the sun is 700,000 kilometers, it does not seem to be in danger of becoming a black hole in the future. The sun is not big enough to become a black hole. Okay? And that's how we use scientific notation and our rules for exponents to answer these types of problems. And the keyword for this particular lesson would be sun devil. Okay, the keyword is sun devil, or the secret word is sun devil. Thank you for watching.